So yeah, as I mentioned, I will be presenting this paper because the original presenter kind of bailed out. And I apologize in advance. I didn't really have a lot of time to go super in depth into the paper, but I think it's an interesting paper to discuss and to look at. So I did manage to put together some slides. So yeah, let's start with that. Today we're going to talk about this SOSP21 paper called Exploiting Nil-Externality for Fast Replicated Storage. So the title has some new terminology, Nil-Externality, and I think we all want to have a fast replicated storage. So let's first look at what is Nil-Externality. Right, so based on the So the paper spends quite some time explaining this concept, but in reality, it's nothing really that new, right? So the paper formalizes this concept a lot better, but intuitively, a nil external operation is some operation that doesn't expose the storage state back to the client, back to the user that invoked, this operation. So the operation can still acknowledge, right? So for example, you can acknowledge that, hey, this operation has been completed, but it doesn't really give you the, the state of a system, right? So surprisingly, many systems actually do that. In the paper, they have this lovely table that compares RuxDB, LevelDB, and Memcache, which is really like a single server storage systems. And what they find out is that RuxDB and LevelDB, this storage, this write optimized storage systems, they actually provide like all of their write operations as nil external. So when you do the put, the system will acknowledge that, hey, the put has been completed, but it doesn't give you the result of this, right? So it doesn't give you an error or the state of what has been written. The same with deletes, and they even say operations like read, modify, writes, which are translated into like this internal merge kind of command. So the same stuff happens in LevelDB, and they say that even Memcache does have this set operation which is nil external. Memcache has a lot of other write operations that are not nil external, meaning that they do expose some state. For example, the delete operation may expose an error of a key being not found in a system. So the fact that you tell that the key is not found is the state, right? So the delete is not nil external. Obviously, read operations, right? They, by definition, expose the state. So they're kind of in their own separate categories. They never nil external. Is this clear so far, or maybe I'm going too fast? Okay, so what can we do with this Nilext operations, nil external operations? Well, intuitively, if you are not returning the state of the system, then there is no need to have the state kind of become visible or materialize just yet, right? So if you're doing the put operation, if you somehow made this put durable, but maybe delay this put being visible, then you can save maybe a little bit of time and return to the client faster, right? So in practice, systems still go all the way, even for these nil external operations, and make them ordered and committed and made externally visible before acknowledging to the client. And there is a very good, so this is kind of how it's done, how it's presented in the paper. So if we have a Paxos-like system, the traditional way of doing operations, regardless of whether they're nil external or not, is a client is going to talk to the leader is going to replicate to the followers. Once replication complete, commitment complete, the leader can return to the client. So this is at least like 2 RTTs. So this is 2 RTTs of communication, right? And then the read can happen from the leader in just 1 RTT. even though it's a Nil-External operation, but because we have this leader who knows the order and stuff, we can cheat a little bit here. So why do we do this, right? If our intuition is like, hey, if it doesn't expose the state, and we don't have to like go all the way and make the operations visible, why do we go like all the way and order them and make them visible and everything? And the answer is like very short. It's consistency, right? So if we want the system to be consistent, like strongly consistent in particular, then this kind of not exposing the state like doesn't really bias that much, at least on the first glance, right? So imagine a black box system that doesn't make the state visible like right away. So maybe this put operation, right? It's Nilext, Nil-External, Nil-External. And we try to write this against this black box operation, black box database, and this database, it actually makes these operations, Nilext operations, visible at some time later. So it defers the execution of these operations. So if we have such a system and we implement this like naively and blindly, then we do lose consistency, right? The top client here writes X5. Gets acknowledged really quickly from the system, and really thinks that the operation has been completed. However, the state has not materialized to x equals to 5 yet. So another client may start a get operation after the completion of this put operation by the other client, and still get this x equal 3 because this materialization point, right? I'll call it materialization point. It is deferred so much into the future that this get operation managed to sneak in. So obviously this is not consistent, and that's why we do go all the way in and make the operations materialize as part of the actual put, and don't defer this operation, this materialization, this state exposure to a later point of time. So all good so far? So what this paper proposed, what the authors proposed, is to speculate, right? So we can hope that there is not going to be such a read that will kind of get in between your materialization or externalization point and your write, right? So we hope that this doesn't happen. We speculate that this doesn't happen. So no such read will arrive to the system. If that's the case, actually that's how this Skiros system proposed in the paper, and that's how it operates. It has the clients who directly write to all of the machines in the cluster, right? So maybe you have 5 machines, leader and 4 followers. So the client is going to write to all of them, and when it receives sufficient number of replies for this write, it just says, okay, the operation is complete. I know it will not be lost, right? It has not been ordered yet. It has not been executed in the state machine, but the client, in this one RTT, it kind of moves on and hopes that there is not going to be a read that kind of gets in between its acknowledging the client moving on and the result actually becoming externally visible. So in the process, in between of all of this, in the background, the leader is going to finalize this operation, assign the order, replicate, commit, do all of that stuff. But this happens kind of in the background at the time when the client may have already received the acknowledgement. So in a sense, all they do here is they make this operation, each write operation that's Nil-External, they ensure it's durable, they ensure it doesn't get lost, but they don't wait for it to get proper order or replicate. Well, it is replicated, but actually fully commit into the system. So when the read comes in later, right, after this background process has ordered and committed the operation, Again, the read always is going to come in to the leader in the Skeros system. So the read is going to take one round trip time and will read the result of this operation. Right. So all good, if we can, kind of believe that this read always is going to come this late in the process. So what if the speculation that we used here kind of goes wrong, right? So if there is a read that tries to access a non-externalized command, right? So the command that has been made durable to the machines, but hasn't been properly ordered and committed yet and executed against the storage, then in Skeros systems, in Skeros protocol, this read operation, this non-Nil-External operation, will actually force the synchronization. Right? So in this case, this read is going to take 2 round trips, right? It will get to the leader. The leader is going to be like, oh, you're trying to access the key that I know I'm still busy ordering and committing. So, or maybe I haven't even started to order and commit this key. So this will actually force the leader to then take, whatever the buffer it has of all these uncommitted operations and assign the order and commitment. So, puts this one extra round trip time to synchronize with the followers and then return to the clients. So hopefully our speculation is correct. Then we can do the reads we can do reads in one RTT. If our speculation is not correct, then it will be 2 RTTs of latency. So that's kind of the intuition for the Skeros system. Any questions or comments so far? All right. So at this point, I borrowed some of the slides from the author's presentation to kind of go a little bit more in depth in how the protocol actually works. So we start, the client interacts with the system, right? Each machine, each node in the system has 2 types of locks, the durability lock and the consensus lock. So the consensus lock is going to be like all of the committed and ordered, like finalized operations. The durability lock is kind of a temporary buffer that stores the operations that the client sends to all of the machines, but the operations that haven't been fully ordered and committed yet. So we can have this client, let's say it sends this operation A. The machine 1 is the leader as designated by this like L letter in the orange color. So it will send this operation A, it will try to communicate with all of the machines. Maybe it's successful with this 4 machines, and they reply the acknowledgement back, right? So in Skeros, you actually want to have a supermajority quorum. So it's not enough for you to get the 3 replies, you need to have 4 replies, and we'll get into this, into why a little bit later. But let's say there's 4 machines, they successfully received this operation A, they replied back to the client. At this point, the client can move on and do something else, right? So the operation is durable, but it has not been properly ordered and committed yet. So maybe some other operation, maybe this client, then the same client in this case probably goes in and writes another operation B, right? And again, it was successful in 4 nodes out of 5, and it moved on. So now we kind of have this a durable lock with 2 operations, A, B on the leader. One important thing I forgot to mention is it's not just the 4 machines that require to answer, the leader must answer as well. So the quorum from the client perspective has to be a supermajority that includes the leader node. The reason why we need the leader node is because the leader is actually the one who's going to be doing the actual final ordering, right? So at some time, on some timeout, on some batched interval or whatnot, the leader is going to look at its durability lock and say, oh, I have A, then I have B, and it's going to essentially use its order, the order in which it received, to move these operations into the consensus lock, and then run view stamp replication in this case to replicate the, essentially the ordering to all of the, well, at least to the majority of the machines, right? So once the majority has been reached, the leader can commit and clean the durability log, right? So it's very important to clean this durability log because that's how the leader is going to determine whether the read or like, any non-nil external operation actually tries to interact with something that hasn't been committed but already acknowledged, right? So if we have something here, let's say operation C, and we try to read C, then we need to commit C before we can read this. So that's how it will determine whether it needs to go into this slow pass and do the like another explicit synchronization to commit C into the consensus log. Okay, so yeah, that's kind of the happy case, more or less, scenario. The problem with this approach is the leader failure, right? Because the clients write to these replicas directly, but they still use, they must include the leader because they use, the system uses the leader's order as the order that's going to be committed in this consensus log and the order in which the operations are going to execute against the state machine. So naturally, what happens if the leader fails before it manages to replicate this, right? So if leader fails before, replicates in this from durability log to consensus log, replicating the order. So we need to recover the order, right, from the remaining nodes. I'm not going to go into too much details, but the basic idea is that if the operations are concurrent, right, then how we order them, it doesn't really matter. But if there is a happens before relation between the two operations, then we need to recover this partial order. And this is why we need to have the supermajority quorum, because essentially we want to have this like the partial order preserved. So let's say we have 5 machines, right? If 2 machines, we have to commit the operations into 4 machines, right? Not commit. We have to make them durable in 4 machines for the client to be able to move on, right? So if one operation happens before another, then it has to appear in the same partial order in 4 out of 5 nodes, right? So even if we crush 2 of these nodes, then the majority of the remaining nodes will still have the correct partial order. So that's kind of borrows a lot of ideas from fast Paxos and probably even ePaxos more than fast Paxos. So in this recovery process, or the literature, it does construct the graph DAG of dependencies and use that to kind of recreate the order. Okay, another thing that I do want to mention is the availability of the system, right? Because we require this supermajority, in the machine in a cluster of 5 machines. That means 4 out of 5. So, 4 nodes. If 2 nodes fail, then we cannot reach the supermajority. So, at this point, we either get stuck forever until we recover enough machines to get the supermajority, or we go into the slow pass and essentially kind of ditch the whole like Nil-Externality idea and just talk to the leader and make the leader, do a regular view-stem replication, multi-paxos route protocol, whatever you have. So that's kind of, I guess, one of the downsides of having the supermajority. And yeah, now we can move. Do you have any questions, by the way? Okay. So now let's move to the evaluation. This is where I have like the most questions and concerns for this paper given. So the main comparison that they used is Paxos, which I think they mean multi-Paxos, which actually in the paper they say that this is actually a view-stem replication. So yeah, so they compared with Paxos no batching and Paxos that's batched. Their system, Skirus, is batched in the sense that the leader is going to wait for some number of operations to accumulate in a durable log before it will, transfer them into the consensus log and run the Paxos protocol, the instant replication protocol, to commit them in the consensus log. So they ran the experiments on M5ZN bare metal Amazon EC2 instance, which I had to look up. Has like 48 cores and 192 gigabytes of memory. So to me, it seems like an overkill. Try to find a multi-Paxos implementation that can use 48 cores. I'm pretty sure that's not going to happen. In the figure A, they show the latency versus throughput for a workload that only has Nil-External operations, which means these are only writes, there are no reads, and these are the writes that are Nil-External. In this kind of configuration, we can see that Skirus, the system proposed in the paper, does outperform batch Paxos, both in terms of throughput, and also has lower latency, obviously because it kind of speculates and doesn't have any reads or anything to break the speculation assumption. So the performance is slightly, the throughput is slightly bigger. I speculate that's because the clients can actually write to all of the nodes. So some of the load is better distributed across the cluster versus in like multi-Paxos, the client will talk to the leader, and then the leader is going to have to replicate the same payload then to the followers. So kind of puts more work on the leader node to actually replicate the payload, versus in Skirus, all you have to do is replicate the ordering. So that being said, I would expect a bigger throughput gain because of this better load distribution. On the figure on the right, it's a little bit confusing. They now run, again, only write operations, no reads, but some write operations are non-Nil-External, right? So maybe an operation that does expose state, like maybe, I don't know, compare and set operation from memcache to something, or maybe it does have an error or potential to return an error. So it needs to run, essentially, any non-Nil-External operation needs to run, like if it's a write, needs to run in the regular two phases. It pretty much runs the basic multi-Paxos protocol or RAF protocol, or view-stamp replication in their case. So they claim that in the worst case scenario, when all operations are non-Nil-External, Skirus kind of degrades down to the performance level, the throughput level of multi-Paxos. But in the best case scenarios, it's almost twice, like 1.95 here. So I guess about 2 times the throughput here. What kind of confused me is why the multi-Paxos throughput right now is 40K ops per second versus here they managed to reach about 100. I'm not entirely sure. And I think this latency is from a different figure. I miscut the figure from the paper. So that's kind of one interesting thing. I'm not sure why the throughput here is 40. Here they went all the way to 100 and something. And this set of experiments shows the latency for Skirus and multi-Paxos. In this experiment, they do have Nil-External writes and then some percentage of read operations. So when the workload is like 90% writes, Paxos has, or multi-Paxos has a lot higher P99 latency. It does have a higher average latency as well than Skirus, but the P99 is like where the biggest difference is. When the write percentage is small, when it's mostly reads, actually we can see that Paxos's latency is almost the same. It's like the same as the Skiris's latency. So, but of course not the P99. So the P99 is still high up. Similar picture really happens with the Zipfian distribution of keys. And finally, I want to share the YCSB throughput figure comparing against Paxos and Skiris for different workloads. And pretty much everywhere except maybe this workload C, we see that Skiris does outperform Paxos. Right, so in workload B, I believe there is a very small number of what is it? Writes, I believe. So it's mostly read heavy workload. Yeah. And that's all I have for the slides.